Hello everyone, welcome to today's video on acids, bases and salts. The first question, why do we need to study about acids, bases and salts? I'll show you so many things around us that are actually acidic or basic or they are salt. In fact, all of these things are very useful in our day-to-day life. Talk about citrus fruits like oranges, lemon, lime, amla, they all have citric acid. The stomach acid, that is hydrochloric acid, play a very crucial role in the process of digestion, is again an acid. Most of the fertilizers are acidic in nature. Perfumes, which are otherwise neutral, but if they have an ingredient like lime or lemon, they become acidic in nature. Not just acids. If we talk about bases, there are so many bases around us. Starting from washing soda to baking soda, bleaching powder, toothpaste, antacids, they are all bases. Salts, needless to say, we have the common salt, which is like an essential ingredient in our cooking. So what are we waiting for? Let's get started and understand more about acids, bases and salts. In this video, we will learn about acids, bases and salts, acid-base indicators, reactions of acids and bases, strength of acids and bases, the concept of pH, and chemicals obtained from common salt. What is an acid? A solution that has an excess of hydrogen ions and are sour in taste. Think of the citrus fruits like sweet lime and lemon. They are sour in taste and they are acidic in nature because they have citric acid. What do we mean by excess of H plus ions? That actually means that acids dissociate in water to produce hydrogen ions. In fact, if you talk about a strong acid, it ionizes completely to produce hydrogen ions and negatively charged ions. Now, what it means is anything that has a lot of excess stock of hydrogen ions. Now, if it gets a chance to release some ions, let's say because of ionization or something, so what will it do? It will release the hydrogen ions, right? So that's exactly what is true with acid. They have excess of hydrogen ions and therefore they tend to release hydrogen ions in solution. Let us now quickly look at the history of acid, and I think it would be interesting to know about it. Well, people have been defining acids in many different ways since hundreds of years rather. So looking at this, you can see that there were scientists who were trying to define acids in 1700s till 1900s. So it's like so many years and people were just trying to figure out what exactly were acids. Long time ago, the Greek, they defined acid by taste. So they said that anything that tastes sour is acid, which is partially true today, but it is not like the basic definition of acid. A couple of years later, around 1776, Lavoisier told that acids should be defined by structure. So any structure that has oxygen is acid. But again, to his contrary, a few years later, Davy said that it was not on the basis of oxygen that we can define acid. However, Davy did not give any specific definition of acid, but all he did was he tried to tell that the definition that Lavoisier gave was incorrect because he found that there were some acids that did not have oxygen in their structure. Again, a few years later, Vaughan came up with a new definition of acid, and he said that one with hydrogen is acid. So he said that presence of hydrogen tells us about the acidic nature of a particular substance. Again, few years passed by, then came Arrhenius. He said that substances delivering hydrogen cations to the solution are acids. So he completely relied on water. So he said that if you have a substance which you have to identify whether it is acid or not, so you will have to dip that in water and see if it is releasing hydrogen ions. So his definition was completely on the basis of like water, like how does it behave in water. But his thought was that any such substance which releases hydrogen ions in water is acid. Now, later came up Albert F.O., who in a way supported Arrhenius' definition, but he tried to generalize the definition to cover aprotic solvent. Because Arrhenius' definition was very specific to water, like in water, if a substance behaves this way, it is acid. But Albert said that that doesn't work, right? So we need to take into consideration all the other type of solvents as well. So he kind of extended Arrhenius' definition to aprotic solvent. Now you may ask, what is aprotic solvent? Now solvents are of two categories. One is protic solvent, the other one is aprotic solvent. So protic means a solvent that contains hydrogen ions or protons. So that's why they are called protic solvent. And in exactly similar way, aprotic solvents are those which are without protons or without hydrogen atoms. Therefore, there are no oxygen-hydrogen or nitrogen-hydrogen bonds. So they are aprotic solvent. So obviously water falls under the category of protic solvent. So therefore Albert F.O. said that, Arrhenius' definition is true, but this is true even for aprotic solvent. Okay. Finally, a few years later again, around 1923, Bronsted and Lowry, they said that ability of acids to donate hydrogen ions or protons to bases which accept them. So they said that yes, this is true, that substance that has a tendency to release hydrogen ions are acids, and these hydrogen ions in turn are accepted by some other set of substances, and they are called bases. And today the definition that we learn is also on the same basis, that any substance that releases hydrogen ions or that has excess of hydrogen ions are acids. So if you look at this example, like when an acid reacts with a base, acid like hydrochloric acid, when it reacts with a base like sodium hydroxide, what happens? Hydrochloric acid tends to lose H plus ions, right? And then these H plus ions are accepted by the base, that is OH, and OH and H plus, they combine to form H2O. So left behind are Na and Cl, so they combine together to form the salt. So we very clearly see here that how acids lose hydrogen ions and how bases accept them. So this is how acids came into picture and they were defined. Acids are present in a wide variety of things around us, like vinegar, aspirin, vitamin C, soda water, soft drinks, citrus fruits, stomach acid, fertilizer, explosives, car batteries, and the list is too long, isn't it? So this lists some of the acids which are present in most of the common substances that we see around us, starting from vinegar to aspirin to soft drinks, soda water, in fact even the stomach acid which helps in the process of digestion, fertilizers, and even car batteries. There are so many different types of acids present in different forms in different objects around us that a classification of acid became necessary. Acids are classified into different types based on different factors. On the basis of origin, acids are of two types, organic acids and mineral acids. On the basis of strength, acids again are of two types, strong acids, weak acids. On the basis of concentration, they are again of two types, dilute acid and concentrated acid. And on the basis of state, acids are of three types, solid, liquid, and gas acids. Organic acids. Organic, anything that is derived from living organisms, are generally called as organic. So these acids are also derived from living organisms like plants or animals. Now generally they are weak acids and therefore they are not harmful for living organisms. So examples of organic acids would be citric fruits. So citric acid is present in fruits like oranges, lemons, etc. Besides that, acetic acid in vinegar, oxalic acid in tomato, tartaric acid in tamarind, or lactic acid in milk or curd. So these are all examples of organic acids, because if you look at them, they are all derived from fruits, vegetables, milk products, and these are all like derived directly or indirectly from plants and animals. Now, they are weak acids, not at all harmful for living organisms. On the other hand, we have inorganic acids, which are also known as mineral acids. Now, they are quite strong, they are dangerous and corrosive as well. So, examples of such acids are hydrochloric acid, sulfuric acid. So, we normally use them in our chemistry laboratories, right, to perform different experiments. But these acids are very harmful for us, and therefore we do not consume them in any form. Let's see, what do we mean by strong and weak acids? So strong acids completely dissociate into its ions in aqueous solutions. Now this is important, completely dissociate. Some examples of strong acids are hydrochloric acid, sulfuric acid, nitric acid. So if you look at these acids, for example, if you talk about hydrochloric acid, this will completely dissociate to form H plus and Cl minus. And these ions which are formed, hydrogen ions or chloride ions, they do not recombine. So these are examples of strong acids. On the other hand, if you talk about weak acids, they do not completely dissociate. So they dissociate, but they dissociate partially into their ions in aqueous solutions. Some of the examples of weak acids are carbonic acid, acetic acid. So if you look at these examples, let us talk about acetic acid, CH3COOH. So they partially dissociate to form H plus and CH3COO minus. So do you see the symbol? This shows that it's not that it completely dissociates into these ions and they never recombine. It's not like that. So here this acid dissociates to form these ions, but these ions recombine to form the acid again. So what we notice is, in case of weak acids, only a small fraction of the molecules ionize to hydrogen ions and acetate ions, and most of it remain as unionized acetic acid molecules. So that's the major difference between strong acid and weak acids. Dilute and concentrated acids. Dilute means low concentration of acids in aqueous solution. That means, let's suppose, so just to remember what is dilute and which one is concentrated. Dilute means when you add lot of water to anything. So you would have heard that your mother or grandmother would scold the milkman for diluting the milk with a lot of water. So when you mix a lot of water into something, that becomes the dilute version. Similarly, when you have less acid and more water, that's dilute acid. So the percentage of acid is less in case of dilute acids. But when you talk about concentrated acids, that means there is high concentration of acids in aqueous solution. So that's like more percentage of acid comparatively in the aqueous solution. Right, so that's the difference between dilute and concentrated. Now for most of these acids, you would have seen that for many reactions it is written dilute HCl. At some places it is written concentrated HCl. That actually means, dilute means you have mixed a lot of water with that hydrochloric acid. Concentrated means you just have that pure concentrated HCl, no water mixed to it. Right? So obviously concentrated hydrochloric acid is a lot more dangerous than dilute hydrochloric acid. Just like how we have 3 states of matter, in a similar way we also classify acids into 3 types based on their state. That is solid acids, liquid acids and gaseous acid. So solid acids examples are HiO3 and sulfanilic acid. Liquid acids are hydrochloric acid, sulfuric acid, and gas acids are carbon dioxide, H2S. So these are all examples of gas acids which are in gaseous form. So an interesting fact in this regard is hydrochloric acid. So what is hydrochloric acid? It is HCl. HCl is also hydrogen chloride, and hydrogen chloride is a gas. So hydrogen chloride is a gas. But hydrochloric acid is liquid. So how do we get hydrochloric acid from hydrogen chloride gas? So basically, when hydrogen chloride gas is dissolved in water, we get hydrochloric acid, which is liquid, which is in the liquid form. So this is when we get H3O plus Cl minus, and from here we get hydrochloric acid, which is in liquid form. What is a base? Bitter in taste and soapy in touch. Now, that doesn't mean that you go and try to taste a base, because that could be extremely poisonous for your health. So do not attempt to do that. Just trust me that bases are bitter in taste. Now, as far as defining a base is concerned, there are two definitions. The old definition says that a solution that has an excess of hydroxide ions is a base. The new definition says that an object that accepts the hydrogen ions is a base. Now, both of these definitions are correct, but if you go to their accuracy, the old definition is correct for 99% of the cases, while the new definition is correct for 100% of the cases. So let's take a look how. Two examples of bases, that is NaOH and NH3. Both of these are bases, and with these two examples we will try to see that the new definition holds true for most of the cases. So let's look at the first case, that is sodium hydroxide, NaOH. So here we see this has excess of OH minus ions, so we can actually see that it has OH minus ions. So that way the old definition is true. We also see that NaOH takes H plus ions to form H2O. So it also accepts H plus ions. How do we know that? When NaOH reacts with HCl, hydrochloric acid, what happens? Hydrochloric acid releases H plus ions, and this OH, it accepts H plus ions and it forms NaCl plus H2O. So basically it accepts the hydrogen ions to form water. So that means the new definition is also true. Now let us look at the second example, that is NH3, ammonia. Now this is a base, but if we look at the old definition, does it have OH minus ions? No. So the old definition is not true in this case. But as per the new definition, does NH3 accepts hydrogen ions? Yes, it does. Let us look at this reaction. What happens when NH3 reacts with HCl? Now HCl again tends to release the H plus ions, and who accepts that? NH3, and it forms NH4Cl. Right? So we see that in this case, even though NH3 doesn't have OH minus ions, but it still accepts the hydrogen ions released by acid. Correct? So that means the new definition is correct. So both of these are bases. In the first case, both old and new definition are true. In the second case, only the new definition is true. So that is why we consider that the new definition is more generic, because it is true in 100% of the cases, but the old definition is true only in 99% of the cases. List some of the common bases which are present in things around us, starting from antacids to deodorants to glass cleaner to the plaster of Paris, laxatives, or even if you talk about very common things which we normally use for baking, like baking soda or dish detergent or drain cleaner or even bleach. So these are names of some of those common bases, and I think it will be good if you know these names, like which are the bases present in each of these things around us. Just like acids, bases are also of different types based on different factors. On the basis of strength, they are of two types: strong base, weak base. On the basis of concentration, they are again of two types: dilute base, concentrated base. On the basis of state, they are of three types: solid, liquid, and gas. Strong base and weak base. So just like strong acids and weak acids, strong base, they completely dissociate into its ions in aqueous solution. So whether it is a strong base or a strong acid, they completely dissociate. So examples of strong bases are sodium hydroxide, potassium hydroxide. So if you look at these, so NaOH, so they completely dissociate to form Na plus and OH minus ions. On the other hand, if you talk about weak bases, they do not completely dissociate. into their ions. Let's look at examples like NH4OH, ammonium hydroxide. So NH4OH, they dissociate but partly dissociate to form NH4 plus OH minus ions. This means that these ions formed, they tend to recombine to form NH4OH. So overall, only a small fraction of NH4OH dissociate into NH4 plus and OH minus. Most of it remain as NH4OH. Right? So that's about strong and weak bases. Let's talk about dilute bases and concentrated bases. So dilute bases, again, low concentration of alkali, that is the base, in aqueous solutions. So exactly, the concept is exactly the same as in dilute and concentrated acids. So examples of dilute bases could be any base which is in the dilute form, like a lot of water has been added to it. Concentrated means high concentration of alkali in aqueous solution. So for example, if you say dilute NaOH, that would actually mean that a lot of water has been added to it. Therefore, the actual concentration of NaOH is very less. So that's dilute. And if you say concentrated NaOH, that means there is no water that has been added to it. Let's also talk about solid, liquid and gas forms of bases. So examples are sodium hydroxide, which is in the solid form, as you can see in this in the picture. They are in the form of these white color crystals. Then you have the liquid form, which is like water, like that's the form. And then you have gas, NH3, ammonia. It is in the gas form, but this is also a base. What is a salt? Not always common salt that we use for cooking. In fact, there are a lot of other salts. In fact, we have a family of salts that are extremely useful for us in some way or the other. Salts are actually ionic compounds which are a result of neutralization reaction between an acid and a base. So let's look at it. Examples of salts. Common salt, of course, which is widely used in cooking and also used as a preservative. You must have observed that a lot of salt is generally put when you prepare a pickle. Can you think of other examples of salts? Like potassium permanganate, which is used to treat a lot of skin infections. Potassium dichromate is another example of salt. In fact, we'll talk about a lot of salts in more detail just now. A quick question that might come to many of your mind: why is common salt called common salt when we have so many other salts? That's because this is one of the most commonly used salt which we use in our day-to-day life, and that's why we call it common salt. So common salt chemically is sodium chloride, NaCl. Salts exist in many different colors. For example, if you talk about sodium chromate, it's yellow, potassium dichromate orange, potassium ferricyanide red, and you can actually see so many multiple colors starting from yellow, orange, red, mauve, blue, purple, green, white, or even colorless like magnesium sulfate, heptahydrate. So these are examples of some salts with their respective colors, just to give you an idea that salts are not of any specific color. A lot of us just think about sodium chloride, that is common salt, which we use in our cooking and for eating purposes. So salt means it's always like sodium chloride, but that's not the case. There are so many other types of salts which are available in so many different colors. We are given an object. How do we know if this is acidic or basic? Will you say that this is acid just because your teacher told you so? That's not fair. So this is exactly when we talk about acid-base indicators. There are certain substances which react very differently with an acid and very differently with a base, thus enabling us to know which one is an acid and which one is a base. The most popular and most common acid-base indicator is the litmus solution. You must have seen the litmus papers, the blue litmus paper and the red litmus paper. So the easiest thing to test, the easiest way to test an acid or a base So what happens in an acidic solution? The blue litmus paper turns red. So if you can see here, this was a blue paper and it turned red in contact with an acidic solution. Similarly, just the opposite happens with a basic solution, that is a red litmus turns blue in a basic solution and the color doesn't change in a neutral solution. And this is how we can test whether a particular solution is acidic, basic or neutral in nature. So these are just indicators. They just tell you whether this substance is acidic or basic. That's it. Another popular acid-base indicator is red cabbage leaves. So have you ever seen red cabbage? Normally the cabbage is green in color. But if you go to some supermarket or some market, you would see this red colored cabbage. So their leaves, they also act as indicators. So their leaves turn red in acidic solution, green in basic solution, and blue if the solution is neutral. So these are certain things that you need to know, like, what would be the color if the particular substance is acid, base, or, neutral. So these colors are something that you should know. Another indicator is turmeric, which is very easily available in our kitchen, because especially in India, we use turmeric in cooking almost, like I would say more than 50% of the dishes we use turmeric, which is also called haldi. Now, in acidic solution, the turmeric, so if you prepare a strip of turmeric, like, that's a turmeric strip, so it is yellow if the solution is acidic in nature, and it turns red if it is basic in nature. So you would see that often if you mix something which has base, because a lot of substances that we use for cooking has base, right? So if you mix those substances with turmeric, you would notice a change in color. Another one is colored petal of some flowers such as hydrangea and geranium. So these are some flowers which are not, I would not say that they are very commonly available everywhere, but yeah, their petals act as acid-base indicators. Not just that, we have some chemicals like phenolphthalein, which acts as a very good acid-base indicator. So this is how the structure of phenolphthalein looks like, and with this, in acidic solution it is colorless, and in basic solution it turns pink. And that's how we identify between acid and base. Not just phenolphthalein, we also have methyl orange, which behaves differently with an acid and a base. So in acidic solution it turns pink, and in basic solution it turns yellow. So that is why I've put these pictures here, so that it becomes easy for you to get a perception of how the color change happens. So that's methyl orange. So till now we have spoken about so many acid-base indicators where a color change tells you whether the substance is acidic or basic in nature. So let's look at this experiment with onion, which very clearly shows that how onion acts as an olfactory indicator. So what we do is, in fact, if you want, you can also try out this experiment at your home, and all you need is some finely chopped onion along with a cloth strip, and place it inside a bag like this, and then tie the bag really tight. So tie it tightly and leave it like that overnight. Right? Now, what do? You take two strips, strip 1 and strip 2, like these. So on strip 1, you pour hydrochloric acid. Now, before I go ahead, so from where did we get these strips? This strip is like obtained from this particular piece of cloth. For example, you leave it tonight. So tomorrow morning, you take that strip of cloth, tear it into two pieces. So this is your piece 1, this is your piece 2. So on piece 1, you pour some hydrochloric acid. On piece 2, you pour some sodium hydroxide, which is base. Right? Now what do? Rinse both of these cloth pieces with water. And then what do you observe? You observe that even after rinsing with water, you see that strip 1 still smells, strip 2 no smell. How did that difference happen? So this shows that onion, when it reacts with acid, the smell exists, but when it reacts with base, the smell goes off. So, and that is why onion is called as an olfactory indicator, because here we see that there is no change in color, but there is a change in smell. So there's a change in smell when it is a base, but there is no change in smell when it is an acid. Right? So these kind of substances whose odor changes in acidic or basic media, they are called olfactory indicator, and onion is one example of olfactory indicator. Another example is vanilla essence. We often use vanilla essence when we bake a cake, so it gives a very nice fragrance, right? Let's perform an experiment with vanilla essence. So what you need to do is you take two test tubes, test tube 1 and test tube 2. So in the first test tube, you put some hydrochloric acid. So in this we have put some hydrochloric acid, and in this one we have sodium hydroxide. And in both of these test tubes we have dilute vanilla essence. That means vanilla essence diluted with water, mixed with water. Now, once we pour hydrochloric acid and sodium hydroxide in these two, we really shake them well. Now, after shaking them well, so in both of these, we anyways have dilute vanilla essence. So that's there in both of these. Now, we shake them really well. So shake well, that's important. And after that, we see that in test tube 1, it still smells. The smell of vanilla essence is still there, but in case of test tube 2, there is no smell. So that shows that the odor of vanilla essence goes away when it reacts with a base, but it stays when it reacts with an acid. So you see, most of these olfactory indicators, they have a very very strong smell of their own. For example, the smell of vanilla essence can be very clearly felt. Similarly, the smell of onion is really strong and you can really feel that smell, right? So generally these kind of substances which have a very strong and typical smell, they act as olfactory indicators. So it's time for a question. So now that we know about acid, bases, and we also know about these indicators, let's try this out. You have been provided with 3 test tubes. One of them contains distilled water. The other 2 contain an acidic solution and a basic solution respectively. If you are given only red litmus paper, how will you identify the contents of each test tube? Okay, so let us first mark these test tubes as 1, 2, 3. So out of these 3, one of them has distilled water, one has acid, one has base. So we have to identify which one is what. Since we have a red litmus paper, all that we can do to start with is dip red litmus paper in all the 3 test tubes one by one. So wherever it turns blue, that is base, because if a substance is basic, then the red litmus turns blue. So one thing is clear. So let us suppose, let's just assume that in test tube 1, the red litmus paper turns blue. So that means in the test tube 1, we have a base. So 1 is sorted. Now what are you going to do? How will you identify that out of 2 and 3, which is acidic and which is distilled water? So distilled water is basically neutral. So how will you identify that? Because for that, you would need a blue litmus paper. Do you have a blue litmus paper? Yes, we do have, because the red litmus paper which I had, it turned blue, right? So now I also have a blue litmus paper. So now we will dip this blue litmus paper. So we dip blue litmus paper in 2 and 3. So wherever we see there is no change in color, that is distilled water. So if there is no change in color, that is distilled water. So let us suppose that in test tube 2, there is no change in color. That means that is distilled water and is neutral. And therefore the last one, we will definitely see a change in color, that it will turn the blue litmus to red. So that's going to be acidic. So in this fashion, we can determine which is acid, which is base, and which is neutral. So friends, what do you think about water? Is it an acid or a base? Well, Water can be considered as an acid or a base depending upon how you look at it. It can behave like a base in certain reactions or an acid in certain other reactions. So let's take a look. An important note, distilled water is always neutral, but the water that we get from the tap or the rainwater, they all have ions in them which make them acidic or basic. So let us see how water behaves both like an acid and a base. So we would see that in some reactions, water takes hydrogen ions, so it behaves as a base. While in some reactions, it gives hydrogen ions and therefore behaves like an acid. So let us look at this particular reaction. So here we see that water reacts with water to form hydronium ions and OH minus ions. Right? So what's happening in this particular reaction? So here we see that this particular water, H2O, this forms H3O plus. So while it forms H3O plus, what's happening? It is taking in one H plus. So in this process, it is taking in one H plus. So accepting H plus ions, that means it is acting as a base, right? But when you look at this particular water molecule, what's happening? This particular water molecule is giving out H plus ions, right? So and that's the H plus ion which this particular water molecule is accepting. But this water molecule is releasing H plus ions. Therefore, this is behaving like an acid. So in this one reaction, we see that one water molecule is behaving like a base because it is accepting the hydrogen ion which is released by the other water molecule. So the other water molecule is behaving like an acid. That is why it is said that it all depends on how you look at it. So water has the ability to behave like an acid. It also has the ability to behave like a base. It has certain properties similar to acid, certain similar to base. And that's why there are so many questions which arise in our mind with regards to water. Having said that, when it comes to distilled water, it is all pure, it has no ions within it, so distilled water is always neutral. But when we talk about other water like the tap water or the rain water, so they all have ions in it. In fact, the drinking water, the water that we drink, that they also have ions in it because those ions are useful for our body needs minerals. So they are all not neutral. Only distilled water is neutral. Now that we have been talking about acids and bases for quite some time, let us see how do some of the popular acids and bases look like. So here we take examples of some of the most popular acids like sulfuric acid, hydrochloric acid, nitric acid, acetic acid, and all of these. How do they look like? They look somewhat like this. So they are in the liquid form. So I'm sure that you would have seen all of these acids mostly in your science laboratories, right? So they are like packed inside jars like this and they look like water. So liquid form. So that's how they look. On the other hand, we have some bases like sodium hydroxide, potassium hydroxide, and they exist in solid form. So they look somewhat like this, like you can say just like naphthalene balls. That's how they look like right now. So they are like crystal form, white in color. So this is how they look like. They're solid. Again, when you talk about some other bases like calcium hydroxide or magnesium hydroxide or ammonium hydroxide, they are all in powder form like this, like white color, powdery form. Right? So this is how some of the popular acids and bases look like. How do acids and bases react with each other? Now, this is a very popular reaction and is often known as neutralization reaction. Why? That's because acid and base combines with each other to form salt and also to neutralize each other's effect. So basically the acidic nature of acid is neutralized. The basic nature of base is also neutralized to form neutral salt along with water. Okay, so let's perform this simple activity to understand how neutralization takes place. So let's suppose you have a test tube and you have put, say, approximately 2 milliliter of dilute sodium hydroxide, right? So we know that this is a base, but that is something that we know. But in order to prove it, So we can use an indicator. So the indicator that we have used here is phenolphthalein. So what we do initially, we add phenolphthalein indicator and we just add 2 drops of phenolphthalein. As we do that, we see that what happened, the color changed from colorless to pink. Okay. So why did that happen? Because that's the nature of phenolphthalein as an acid-base indicator. So it turns colorless, it turns pink in color whenever it is with base. Fine. Now, as next step, what we do is we add dilute HCl. So now we add dilute HCl and we continue adding it drop by drop. So it's not that we just add 2 drops or 1 drop. We keep adding it drop by drop. So what do we notice? So we notice that the color changes from pink to colorless after some time. So now I can ask you that why do we see this change now? Now what happens is when we add dilute hydrochloric acid, a reaction like this takes place. Sodium hydroxide combines with hydrochloric acid to form sodium chloride and H2O. So basically the basic nature is lost, the acidic nature is also lost. Right? So they neutralize to form a salt. So as a result, this is no more basic. So phenolphthalein is pink in color only when this solution which is there is a base. But right now the basic nature of the base is lost. So as a result, the phenolphthalein becomes colorless. Right? Now an interesting thing to note here is, now this reaction takes place in this fashion that since we continue to add this HCl, right? So initially the effect of HCl is neutralized. Why? Because we also have NaOH, sodium hydroxide, which is a base. But after all the NaOH is over, because NaOH is limited here, we just have 2 ml of NaOH. But HCl we are, kind of adding drop by drop. So after all the NaOH is over, then we see the change in color. That is, then only we see this colorless thing. Because this colorless thing means that it is acidic in nature. That is when phenolphthalein turns colorless, right? So initially it is like neutralization. So it's like there's no change in color because it is all neutral, right? But after some time what happens is the base is all used up because we have limited stock of base. Base is like in limited quantity. So then what are we left with? We are left with acid, that is dilute HCl. And in acid, what is the color of phenolphthalein? Colorless. So that is why while performing this experiment, you will notice that this change in color doesn't happen immediately after you add dilute HCl. So initially you do not see any change. That is because initially when you are adding dilute HCl, its effect is getting neutralized because of the presence of the base. Only after some time you will see this change in color because after some time this NaOH has been all used up. So there is no more NaOH. And then you see that the color has changed to colorless, which means that the solution here is now acidic in nature. Now, for your better understanding, what you can do is you can again start adding NaOH drop by drop. So now basically before the step 3, now you have this acidic solution, right, which is colorless. Now you start adding NaOH drop by drop. What would you see? So initially again you will not see any change because initially when you are adding NaOH, it is getting neutralized by the HCl which is there in the test tube. But after some time what happens? The HCl is all used up. So now what you have in the test tube? NaOH, which is a base. And what is the color of phenolphthalein in a base? Pink. So after some time you will see that the colorless thing is changing to pink again, which means that now what you have here in the test tube is a base. That is, now all you have in the test tube is NaOH. So this is a very good experiment to understand how this entire neutralization reaction takes place. And it's not that as soon as you add acid or base immediately there's change in color. There is not, because initially if there is a base in the test tube already and if you are adding acid, so initially they are neutralizing each other's effect, so you do not see any color change. So if you have not understood this experiment, please recap it, watch it again, please understand this. This is very, very important. So moving ahead with how do acids react with metals. Now this is again something very, very important. So normally what happens is acid reacts with a metal to form a salt, and hydrogen gas is liberated during the process. Right? So what we will understand here is how exactly this reaction take place. Always remember one thing, acids, they are always willing to lose H plus ions. So that's how they are defined. They always have like excess of H plus ions, and therefore they are always ready to lose those H plus ions because they have it in abundance. So at any situation they are ready to give H plus ions, right? So how do you think they would react with metals? Let's look at this. Let us take this example. Let us suppose we have this acid, hydrochloric acid, and it reacts with a metal, say sodium. So what do you think should happen? So how will a salt be formed? Now what will happen is the metal displaces the hydrogen from the acids. So if you look at the acids, they will have these hydrogen. For example, if you talk about HCl, H2SO4, HNO3, you have the hydrogen atom. So the metal will actually displace this hydrogen atom and take its position. So in this case, what will happen? Sodium will kick out H from HCl and will take its position and will form NaCl. And what will happen to this hydrogen? This will be liberated as hydrogen gas. So this is how a salt will be formed. Now the question is, does that mean that if an acid reacts with any metal, so that metal will be able to displace the hydrogen? No, not really. So there is a catch there. So this is the reactivity series of metals, right? So now this series tells us which metal is more reactive than which metal. So looking at this series, you see that potassium is the most reactive. Then comes sodium, then calcium, magnesium, and so on. Now this means that anybody, so we will take this analogy. Let's suppose that there are two players. So somebody who is more powerful will be able to displace the other person with his or her power, right? So the powerful wins. So that analogy works here. So if a metal is more reactive than hydrogen, where is hydrogen in this series? This is where hydrogen is placed. So any metal which is more reactive than hydrogen will be able to displace hydrogen and take its position. But any metal which is less reactive than hydrogen will not be able to do that. So here in this case, if you see sodium, where is sodium? It is here. So sodium is more reactive than hydrogen. So anything which is above hydrogen, they are all more reactive than hydrogen. Right? Let's take one more example. Let us suppose if you talk about this reaction, zinc plus H2SO4. So here, where is zinc and where is hydrogen? So zinc is here. So zinc is above hydrogen. So zinc will be able to displace hydrogen. So zinc kicks out hydrogen, takes its position and forms zinc sulfate. But if at all we set up a reaction like this where silver plus H2SO4, what will happen? There will be no reaction because silver will not be able to displace hydrogen and take its position. So that is the simple logic in this case. So you need to know the reactivity series in order to, understand how the reaction will take place. Now let's see how do bases react with metals. Now bases react with some metals to form salt and hydrogen gas. So the reaction is similar, but the major difference is that, like in case of acids, like most of the acids react with metals to form salt and hydrogen gas, but that's not the case with bases. Only with some metals they react. Some metals like zinc and aluminium, they react. So let's look at this example. Zinc plus NaOH forms Na2ZnO2 plus H2. So here it forms a salt plus hydrogen gas is liberated. Now this is an important point to be noted, that bases do not react with all the metals to form salt and water. Now if I ask you, can you guess why? That why is it that with acids, most of the acids react with all the metals to form salt and hydrogen. But why is it not so with bases? Let's understand this. Now, when we talk about acids and metals, now we all know that metals, they have a tendency to lose electrons. Right? All metals, they have a tendency to lose electrons. Correct? Now, if I talk about acids, what is the tendency of acids? Acids have a tendency to lose H plus ion. Right? What about bases? Bases have a tendency to lose electron or to gain H plus ions, right? Now, what happens if I am talking about reaction between acids and metals? Then this hydrogen ion accepts this electron and they form H2, that is hydrogen gas. But if I am talking about reaction between metals and bases, both of them have a tendency to lose electrons. So who will gain that electron? Nobody to gain the electron. And as a result, there is no preferred direction for the electrons to go because everybody is willing to lose electrons. Nobody is gaining electron. So the reaction will not be able to take place, and as a result, in most of the cases, the reactions do not take place, and as a result, bases do not react with most of the metals. In fact, zinc and aluminium are few exception metals which react with bases. In fact, zinc and aluminium, these are examples of few metals which react with both acids and bases, and as a result, they are termed as amphoteric. Because I'm pretty sure all of you know the answer to this now. As we all know that metals like copper and brass react with acids to form poisonous metal oxides and hydrogen gas, and therefore it is advised not to store such acidic substances in these metal vessels. So how do metal carbonates and hydrogen carbonates or metal bicarbonates react with acids? So metal carbonate or bicarbonate react with acid to form salt plus carbon dioxide plus water. So you would have noticed something very distinctly, that whether the acids react with the bases or they react with metals or they react with metal carbonates or bicarbonates, the product is always a salt, but the byproducts, like the other products, keep changing. For example, somewhere it is water, somewhere it is hydrogen, somewhere it is carbon dioxide, somewhere it is like a mix of carbon dioxide and water. So let's look at few examples. Let's say Na2CO3, that is sodium carbonate, reacts with acid to form salt plus H2O plus CO2. Similarly, in a similar way, it reacts with bicarbonate or hydrogen carbonate, that is Na8CO3, with HCl forms salt, H2O plus CO2. An important point to be noted here is bases do not react with metal carbonates or metal bicarbonates. So only acids react with these carbonates and bicarbonates, and bases do not. Reaction of metallic oxides with acids. Now metal oxide reacts with acid to form salt and water. Let's see how the reaction takes place. Now, with this reaction, you can see that the reaction is very similar to the neutralization reaction, which clearly tells us that the metal oxides are basic in nature because bases react with acids to form salt plus water, right? Now, let us perform this simple experiment to see how this reaction takes place between metallic oxide and acid. Let us suppose we take a beaker, and in that we take copper oxide, which is black in color. Okay, so the black color thing that we have inside the beaker is copper oxide, so oxide of copper. Now what we do, we add dilute HCl. So dilute HCl is added to it, and as a result, what do we see? We see that the solution turns blue in color. So this blue solution is due to the formation of copper chloride, that is CuCl2. So this is a result of this reaction. When this acid reacts with copper oxide, which was black in color, it forms copper chloride, which is blue in color, and H2O is released. So as a result, you see that there you get a solution which has water, plus the color of that solution is blue due to the formation of CuCl2. Let us now look at the reaction of a non-metallic oxide with a base. Now, in a way, just the way we saw that a metallic oxide is basic in nature, similarly we will see that a non-metallic oxide is acidic in nature. Why? Because when a non-metallic oxide like carbon dioxide, carbon is a non-metal, so oxide of carbon is a non-metallic oxide. So when this reacts with a base like CaOH whole 2, we get CaCO3, that is calcium carbonate plus water. So here also we see that we get a salt, calcium carbonate, and along with that we get water. In fact, if you remember the famous lime water turns milky experiment, where you have lime water, that is calcium hydroxide, in a test tube, and as you breathe out, so you breathe out carbon dioxide, you see that the lime water turns milky. So that is due to the formation of calcium carbonate, which is milky in color. Right? So this whole reaction tells us that it is exactly like a neutralization reaction, which clearly means that a non-metallic oxide is acidic in nature. So non-metallic oxides are acidic in nature, bases react with them to form salt and water. Oxides, which show acidic as well as basic properties, are called amphoteric oxides. Examples of amphoteric oxides are zinc oxide and aluminium oxide. So what you would see is, if acid reacts with zinc oxide, what happens? Neutralization. That is, you get salt plus H2O. So this shows that zinc oxide here behaves like a base because it reacts with acid to form salt plus water. Whereas if the same zinc oxide reacts with NaOH, what do we see? We see that it forms Na2ZnO2 plus H2O. So here it shows that zinc oxide in this case reacts with a base to form a salt plus water. That means here in this case, zinc oxide behaves like an acid. So zinc oxide and aluminium oxide are two such metal oxides which behave as an acid as well as a base, and such oxides are called amphoteric oxides. Oxides which are neither acidic nor basic in nature are called neutral oxides. One of the best example is carbon monoxide. So after learning so much, it's time to try out a question. So metal compound A reacts with dilute hydrochloric acid to produce effervescence. Okay, so whenever you have such tricky questions, focus on every word, because every word gives you some important information. For example, here the moment I talked about effervescence, what does that mean? So whenever something is producing effervescence, that actually means that water is being produced, right? And that's when you have effervescence. The gas evolved extinguishes a burning candle. Which gas can extinguish a burning candle? Carbon dioxide. So this also means that carbon dioxide is also produced. Write a balanced chemical equation for the reaction if one of the compounds formed is calcium chloride. So you also know that one of the product is calcium chloride. So I think we more or less know all the products. So all the products are calcium chloride plus carbon dioxide plus H2O. So these are my products. Right? We do not know which is this metal compound, but we know that it reacts with dilute hydrochloric acid to form this. Now, looking at this reaction, what do you see? You see that the output is a salt plus carbon dioxide plus water. So what happens? Like in what kind of reaction do we have this? So when a metal carbonate or a bicarbonate react with acid, it forms salt, carbon dioxide and water. So that obviously means that this has to be a metal carbonate or a metal bicarbonate. Now the only metal which is involved here is calcium. That means this has to be a carbonate or bicarbonate of calcium. So this has to be either calcium carbonate CaCO3 or calcium bicarbonate, that is CaHCO3. So these are the only two options which will fit in this case. So with that, we can write the reaction, and I think by now all of you know how to balance a chemical equation. It's time to talk about dilution. What is dilution? So we spoke about dilute acids, dilute bases, right? So what does dilution means? When we add water to something. Now adding water to an acid or a base is an important process. Do you know why? Because the process of dissolving an acid or a base is a highly exothermic process. That means a lot of heat energy is generated during this process, and therefore it is a very important process and care must be taken, because there is so much of heat generating out of this process that it can even cause burns. So therefore it is important that we do it in the right way. And what is that right way to do dilution? So even before we talk about that, let us see what happens. I mean, how do we know that the process of dilution is exothermic? So if you take a beaker and if you actually try to dilute an acid or a base, you would actually see that the beaker turns hot, which clearly tells that heat is being generated during the process. Now, it is always recommended that the acid should be added to water and not water to the acid, because when you have, let's say, a lot of acid in a beaker, and even if you suddenly add little bit of water, what will happen? It might happen that too much of it gets generated and it catches fire. The glass container may even break, right? So therefore it is recommended that you take water in a beaker, add acid, and that too very slowly, that too with constant stirring. So when we say that we add acid, it has to be added slowly and it has to be added with constant stirring. So what happens with stirring? So when you are adding acid and you're stirring it continuously, it's like you're mixing it uniformly in that entire solution. But if you suddenly add it, so it might happen that the concentration of the acid immediately becomes very high in that particular locality, and it might generate too much of heat. So constant stirring is important, and adding the acid slowly to water is also important, and you should never add water to the acid. And this is the reason this process of dilution is worth discussing. Quick question time again. Why do HCl, HNO3, etc. show acidic characters in aqueous solutions, while solutions of compounds like alcohol and glucose do not show acidic character? So now I have to ask you a question. So here on the screen you see the structures of all of these. This is HCl and HNO3, and this is alcohol and glucose. Now a quick question. What is that primary thing that we look for in an acidic character? So in acidic character, the first thing that we look for is H plus ions. Excess of H plus ions, it is an acid, right? Now if you look at structures like HCl and HNO3, you clearly see that they have hydrogen, which they can very easily release when in water. So they readily release hydrogen ions in water, and therefore they are acidic in nature. But when you look at the structures of glucose or alcohol, you see that they also have hydrogen, but they do not release hydrogen ion in water. That is because the hydrogen in their case, they are very strongly bonded either to the oxygen or to the carbon, but they are like strongly bonded, and therefore they do not readily come out of the structure so easily, and therefore they do not show acidic character. Now we saw that there are so many acids around us, there are so many bases. So how do we know that which acid is stronger and which one is weaker? And similarly for a base. So that is where we talk about the strength of an acid and a base. Strength of an acid or a base depends upon the number of hydrogen ions or hydroxide ions released respectively. And this is where we also talk about the concept of pH. So let's get started. pH means potential of hydrogen. So it means potential of hydrogen. So pH value determines the acidity or alkalinity of a particular substance. So if you look at the scale of pH, it measures values from 0 to 14, wherein we say that anything which has a pH of 7 is neutral, that is, it is neither acidic nor basic. Any values from 0 to 7, acidic. Anything from 7 to 14, they are basic. So that's how we determine what is acidic and what is basic. Now, and a very interesting question that might come to your mind is, so from where are we getting these numbers like 0, 14, 13 and 12? Because if I say that, okay, for this substance the pH value is 5, we say that, okay, this is acid. But from where are we getting that number 5? So the value of pH basically bothers only about the concentration of hydrogen or hydroxide ions in a solution, right? Because the acidity or alkalinity is all based on the concentration of the hydrogen ions, right? So pH basically is calculated as negative logarithm of the concentration of hydronium ions. So that means if we know the concentration of the ions, then we calculate the negative logarithm of that, and that's how we get these values from 0 to 14. Okay. Now, why is pH important? I mean, why are we even talking about it? Because if we look at our day-to-day life, we see that everywhere pH plays a very critical role. For example, for the survival of plants and animals, we all need a specific value of pH to survive. So our body, so if you talk about the human body, it works within the pH range of 7 to 7.8. Right? So if the pH value gets disturbed, so the functioning of our body also gets disturbed. In fact, if you talk about our surroundings, so whenever the pH of the rainwater is less than 5.6, so if the pH of rainwater is less than 5.6, then that rain is called as acid rain, because it becomes too much acidic in nature. And acid rain is very harmful for aquatic life, not only aquatic life, for so many monuments. For example, the color of the Taj Mahal changed from white to, you would have seen that it has become quite blackish, and that's because of acid rain. If you talk about soil, an optimum pH range for the soil is very, very important for the proper growth of the plants, and that optimum pH range is between 6 to 7.5. If you talk about our digestive system, so our stomach produces hydrochloric acid, because hydrochloric acid plays a very critical role in our digestion process. Now, this hydrochloric acid operates in the pH range of 1.5 to 3.5. Now, you would have seen that sometimes when you eat some oily food or some stale food, you get into indigestion. And during indigestion, what happens is there is too much acid in your stomach, and you get a burning sensation in your stomach, which we often call as acidity, due to excessive acid in the stomach. And why does that happen? Because your pH value inside the stomach, it has kind of got altered, it has reduced, and that's when you feel acidity. And what do you do during such times? You take antacids, because antacids are basic in nature, so they neutralize the acidic effect inside your stomach. Tooth decay. So here again we see pH has a critical role. Do you know how tooth decay starts? So tooth decay starts when the pH of the mouth is lower than 5.5. Because what happens? Normally when we eat, so many a times while we chew food, some of the food particles stay in between our teeth. So what happens? Bacteria in the mouth breaks down these leftover food in the mouth, producing acids. Now when there is too much of acid being produced inside your mouth, what happens? The pH is less. And when the pH is less, what happens? So it's like a round robin thing. So bacteria will act on the leftover food, it will produce acids, pH will be less. As a result, your teeth will start decaying. So what do you need to do? You need to clean your teeth regularly and properly, so that there is no leftover food inside your mouth. Self-defense by animals. Bee sting leaves an acid of pH range 5 to 5.5, which causes pain and irritation. Like you would have seen that, right? Whenever there's a bee sting, there's so much of pain, so much of irritation. Why does that happen? Because of that acidic nature of the sting. Because when it stings, it leaves an acid inside your body, which causes all these problems. And these kind of problems are seen with many of the insect bites or animal bites. So question time again. Do you think that base has hydrogen ions? If yes, why are they base? Now, Obviously, bases have hydrogen ions. They are bases because they have more hydroxide ions than hydrogen ions. So in a similar way, why are acids acids? Because they have excess of hydrogen ions. That doesn't mean that they do not have hydroxide ions. They do have hydroxide ions, but they have hydrogen ions in excess. Similarly, in case of bases, they have hydroxide ions in excess. Salt is not just common salt. There exists a family of salts. In fact, salt is not just produced as a result of neutralization reaction between an acid and a base, but it is also produced when a metal reacts with an acid or a metal reacts with a non-metal. So here we see that salts are formed by chemical reaction between so many different things, like a base and an acid, which is something that we always knew, that a base and acid combines together to form a salt. Besides that, a metal and an acid, just like magnesium plus H2SO4 forms MgSO4 plus H2, or a metal and a non-metal like calcium and chlorine, they combine together to form calcium chloride, or a base and an acid anhydride, or an acid and a basic anhydride. Now a lot of you might be wondering, what do we mean by anhydride? Anhydride basically is obtained by elimination of H2O. Anhydride, that means H2O is removed from something, so whatever is left out, that is anhydride. So when you remove H2O from an acid, it becomes acid anhydride. When you remove H2O from a base, it becomes basic anhydride. So if you look at these reactions, you see that with all of these reactions, the end product is a salt. So we see that salts can form if solutions of different salts are mixed. Their ions recombine and a new salt is insoluble and precipitates. So there are like multiple opportunities or multiple ways in which a salt can be formed. Now, since there are so many different types of salts, let's talk about the family of salts. So we have categorized them into different types. First is normal or neutral salts. So they do not contain any replaceable hydrogen ions. So that's why they are neutral. For example, NaCl like common salt and Na2SO4. There are acid salts. So whenever the word acid comes, that means they have excess of H plus ions. So they have replaceable hydrogen ions in association with the acidic radicals. For example, NaHCO3, NaH2PO4. So the presence of this hydrogen ion tells us that they are acid salts. Then we have basic salts. So when there is higher proportion of base in the reaction between an acid with a base, then that is necessary for the formation of a normal salt. So basically when you have more hydroxides, for example here you have OH, so that tells you that this is a basic salt. Double salts, they are formed by association of two simple salts. So when two simple salts combine together, they form double salt. For example, potassium alum. So if you look at the formula of potassium alum, it is somewhat like this: KAlSO4 whole 2.12H2O. So that's potassium alum. We also have something called mixed salt. So they contain more than one acidic or basic radical. For example, bleaching powder. So bleaching powder is CaOCl2. So that is a mixed salt. So we are not getting too much detail into each of these salts, but these are just to tell you that even in salts, we have so many different categories. Now we will look at complex salt, and complex salts, they dissociate in water to give one simple ion and one complex ion. Again, as I said, not getting too much detail into this, but just for your information that you have so many different categories of salts. So let's talk about the pH of salts. Now we notice that a salt which is made up of a strong acid and a strong base, they are neutral, because the strong acid and the strong base, they kind of neutralize each other effects. But if a salt is made up of a strong acid and a weak base, which one will dominate? Obviously the acid, because the acid is stronger, and therefore the pH of the salt would be acidic. That is, it will be between 0 to 7. Now, in a similar way, if the salt is of a strong base and a weak acid. So which is stronger? Base, and therefore overall the salt would be basic in nature. So it's very simple. The powerful dominates. So if the acid is stronger, base is weaker, so overall the salt would be acidic. If the base is stronger, acid is weaker, so overall the salt would be basic. Common salt is an important raw material for many materials of daily use, such as washing soda, baking soda, bleaching powder, and many more. So we see that there are so many useful products which are obtained from sodium chloride. The first one being sodium hydroxide. So how do we produce sodium hydroxide from sodium chloride? By the process of electrolysis. So when electricity is passed through aqueous solution of sodium chloride, it decomposes to form NaOH, and along with that chlorine and hydrogen gases are released. Now this process is often termed as chlor-alkali process. Why? Because during this process chlorine and alkali, that is NaOH, are produced or they are formed. Now when you look at this entire process of electrolysis, you see that chlorine gas is given off at the anode, whereas hydrogen gas is given off at the cathode, and NaOH solution is also formed near the cathode. So that's how we get sodium hydroxide from NaCl. The next product is bleaching powder. Now, where have you heard that we use bleaching powder to bleach clothes, like bleaching cotton or bleaching linen? So that's where we normally use bleaching powder. So how do you produce it? How is bleaching powder formed? So bleaching powder is formed from chlorine gas. And from where do we get chlorine gas? From NaCl. So from NaCl we get chlorine gas, and this chlorine gas is used for the manufacture of bleaching powder. So when CaOH(2), that is dry slaked lime, when this reacts with chlorine, it forms bleaching powder, that is CaOCl2, and water is released as part of the process. Now some of the uses of bleaching powder, as I said, bleaching cotton and linen in textile industry. It is used as an oxidizing agent in many chemical industries, and another very important use is it is used to disinfect drinking water to make it germ free. That is like a very important use of bleaching powder. Moving ahead with the next product, baking soda, very commonly used in kitchen, especially when we bake a cake or when we are trying to make some crispy pakoras, we use baking soda. So how do you make it? From sodium chloride. So sodium chloride reacts with water and carbon dioxide and NH3 to form ammonium chloride and NaHCO3, which is baking soda. So sodium hydrogen carbonate is baking soda. Okay, why do we use it? Baking soda is used for baking a cake, of course. It's also used in fire extinguisher, antacids. So we normally take antacids when we are suffering from a burning sensation in the stomach due to indigestion or acidity. And that's when antacids help. So antacids contain the base, that is baking soda, and that helps us to feel better. Not only that, we also use baking soda in the batter of idlis or cakes so that it becomes fluffier. For faster cooking as well. Many a times you would see that many ladies would use this trick. So if somebody wants to prepare chole instantly, as in normally when you prepare chole, you need to dip the pulses overnight so that they boil quickly. But if at all you haven't done that, and if you add a pinch of baking soda to the chole, you'll see that it will cook very fast. So that ways baking soda helps in faster cooking as well. From baking soda we get washing soda, and we use washing soda for many different purposes, especially for cleaning activities. So how do we get washing soda from baking soda? So when baking soda is heated, that is NaHCO3 on heating produces Na2CO3 plus CO2 plus H2O. So Na2CO3 is nothing but washing soda, and we use it for glass, soap and paper industries. It is used for manufacture of sodium compounds such as borax, and as a cleaning agent for domestic purposes. Not only that, washing soda is also used to remove permanent hardness of water. So with this we see that there are so many useful products that are obtained from NaCl. So, and in fact, that's one more reason why NaCl is like the most popular salt. And whenever we talk about salt, the compound that strikes our mind is NaCl. With this, we reach towards the end of this series on acids, bases and salts. Do let us know if you liked the video series, and also if you liked them, do share it with your friends. See you all very soon with a new video. Till then, bye-bye.